Hi there. Have a look at this table on the left. So in this table, in each row, you can see the following things. The name of a wrestler, the number of times that wrestler has been a champion, and the combined number of days where that wrestler has been a champion, or like the sum of the length of all their championships. Along with the column that is the rank, and this is ranked by the combined days attribute. So this table is very interesting by itself, but if you look at the right, we have a couple of questions, and let's try to answer them. Which wrestler had the most number of reigns? So for that, you need to go to number of reigns column, right? And you need to mentally sort them, and you'll find out that 8 is the highest number. And therefore, Ric Flair is the wrestler you're looking for. Second question, the average time as a champion for top 2 wrestlers. Now we need to go the top 2 wrestlers. We can guess that pertains to the rank. And then, so we want the average of these 2 numbers. You even have questions such as, which of the following wrestlers were ranked in the bottom 3, which the answers would be all of those. And then after that, out of these, who had more than 1 reign? And you can see that's Dan Severn. So the paper that we're having here is trying to answer questions like this if given a table. As you can see, this is a pretty hard task, and so pretty excited to read this. The paper is called TAPAS, Weekly Supervised Table Parsing via Pre-Training by Jonathan Herzig, Pavel Christoph Novak, Thomas Müller, Francesco Piccino, and Julian Martin Eisenschloss. Full disclaimer, I know these people, so I might be slightly biased. All right, so you've already seen the task. The task is you are given a table and a question, and you're trying to answer that. Now, it's not as easy as that, but the table questions come in different forms, as you have seen. Sometimes you just need to select a cell from a table, like we have here. The first question, I simply, most number of reigns. I simply select whatever that is. So the answer here is already in the table, Ric Flair. And this they call a cell selection task. This is wherever you need to select a cell. The same for these bottom here. So which of the following wrestlers were ranked in the bottom 3, and out of these, which one had more than 1 reign? All of these answers are in the table somewhere. The second thing is what they call a scalar answer. That is when the answer to be computed is a number that is not in the table. So these average time here, which turns out to be 3,426, is nowhere to be found in the table. So there actually needs to be a computation performed by the model. And lastly, you have these things called ambiguous answers. Now, the ambiguous answers refer to a thing where it is a number that you're looking for, so how many, but the number here is in the table. So you can think of this in terms of training data. If you have a task like this and you have training data and you just have the question, you just have this question, and you're given the answer 2, right? You can teach your model either to select this number here, or you can teach your model that would be wrong, right? Because how many world champions are there with only 1 reign? To simply select this cell here is not correct, because that cell, even though the number is 2, it doesn't mean the same thing. It's not counting, right? So the correct program here would be to count the number, to count the cells where there is a 1 here, which is also 2. And they call this situation ambiguous answer. So you might have already guessed that a single model that does all of this needs to sort of have multiple modes. That's exactly what they propose. So they propose a model that takes in the table and the question. And then in the first step, it selects its mode. So the mode is either the cell selection or it is to compute something. And then whenever it's a cell selection, it simply has a component to select cells. But when it's a compute, it needs to decide in the second step what to compute, and then also select the appropriate cells. So this is the model. Now this stuff like this has existed for a long time in these table answering things, but the way we want to do it here is end-to-end with a single deep learning model, of course, because we want to be better than anything else. And the trend in deep learning is to put more and more into one model and to have it end-to-end differentiable. All right, so you see we need multiple components, right? We need some sort of a mode selector, we need some sort of a cell collector, and we need a thing that decides if we are in the compute mode, what computation to be done. Now, let me present the model that this paper proposes. So this paper proposes to embed the question here, so you can see here, that's the question, into a BERT input. So this is a transformer right here. This is BERT or any variant of BERT that you can think of. So the question is embedded as natural language. And then, interestingly enough, the table right here is also embedded as language. We'll get to that in a second. But the question and the table are in the input, and then the model is asked to do two things. First of all, it's asked to do an aggregation prediction. So this can either be one of these programs called count, sum, average, or it can be, as you can see here, none. So no aggregation. So this handles our first two components. It can decide to perform a calculation or none, and if it is performing a calculation, it can decide to do a count, a sum, or an average. Now, of course, the model here is not limited to those computations. You can think of extending this to any further computation. The important thing is that they have a number as an output. Second of all, there is a cell selector. So depending on this aggregation prediction, you need some cells. Like if you want to compute an average, you need the cells to compute an average over. So the cell selector here will select cells from the table. Specifically, it goes by row and column. Sorry, column and row. Since these tables usually they have a header, right? This is the table header where the attributes are listed. It makes sense to first, in a first step, select which column you want to select from. And then, if once you have a column, let's say this column here, in the second step, you say which of the cells you want to select. Now, these can be multiple, but the way the system is set up, it's first a column selector, and then a cell selector within that column. So you can only ever get columns from the same cell in this thing. Let's remember that for later. All right, so this is what the model does. Now let's look at the input. The input to the model is this here. Now this, if you refer from this before, this was in this blue box, and then here you'd have the computation selection, and here you have the cell selection. Right, so this is how you can relate that. So usually if you input something into a transformer, what you want to do is you want to embed this into a token embeddings. So first you want to split everything you put in into what are called tokens. Now tokens are either things like words or word pieces. The important thing is to have a dictionary for it, and each one gets mapped to a to a vector. So this here is your query. You take your query as a string and you tokenize it, and you get the embeddings from the embedding table, and that's your input, right? So it's a sequence of token embeddings. And then you also embed the table. And this I find pretty cool here in this model, and somewhat special, is that the table is actually presented as just natural language. So you can see here, the table is one string. It's just a single string that goes from left to right. It's just the serialized table. So this table right here, you can see these are word pieces. So this table, if I reconstruct it, if I can attempt to reconstruct it, it is going to be a table that has as the headers col1, col2. These are the names. So in our days before, here would be name of the wrestler, and this would be number of days, right? And then here 0, 1, 2, 3. So this table right here corresponds to this string right here. I hope you can make sense of that. So the table is just put there as one long string. And then in order to make the model realize, you know, what the table is, you have these special embeddings. So usually in BERT you have what they're called position embeddings to indicate where in the sequence that is. So in the simplest case, these are embeddings for the numbers 0, 1, 2, 3, 4, and so on. So wherever the position is. This you can all look up in the Attention is All You Need video. I've made that if you are unfamiliar with transformer inputs. Then also the segment embeddings simply indicate what a token is part of. So for every token that's part of the query, you see you have segment 0 embedding, and for every token that's part of the table, you have a segment 1 embedding. This is simply to tell the model, hey, this particular token is part of the question or part of the table. Then you have the new things. So this paper newly introduces the following embeddings: column and row embeddings. Now these, for the question, of course, they don't make any sense, but you have to put something here. So you just put column 0. But for the table, you see there is a column 1 and column 2. And this exactly, so we've seen that this here is the header of column 1, and this is the header of column 2. And then it goes back column 1, column 2, column 1, column 2. And you can see here this 0 is in column 1, and this one is in column 2, and this in column 1 again. And the same for the rows. So you have row 0 for the headers, and then row 1 for the first two numbers, and row 2 for the second two numbers. So this is all of this. So you see these two are in the first row and these two are in the second row. All of this is to tell the model, all of this information down here is to tell the model how this table looks. So if it wants to select the second column from the third row, it would look in this information to see which cell to select. And then the last thing they introduce is this so-called rank embeddings. Now, as we've seen before, if this first column here is maybe the number of days of something, so this is the number of days, and this second one is the number of reigns, so how many championships, the table can only be sorted at maximum by one of them. So you want to sort of, for each cell, you want to tell the model, let's extend that table by two numbers, 4 and 1. So for each column, you want to tell the model the ranking of the numbers. So here it's pretty easy. This is rank 1, this is rank 2, this is rank 3. Further on the left side, this is rank 1, this is rank 2 down here, and this is rank 3. So the model if you give this information, the model will have an easier time to detect, like, give me the top 2 or something like this. Give me the worst, give me the best, give me the highest, and so on. The model will have an easier time doing that. So that's why the rank here, as you can see, the 0 and as also the number 1 are embedded rank 1 and the other two rank 2 because they're just lower. Now I feel they could have given a better example than this table. I feel you could actually put real names here to make clearer, not call 1 and call 2, and I feel you could give a somewhat smarter content, because if you just look at the picture here, you cannot see the correspondence of these rank tokens, because in essence they are exactly equal as the row tokens. But fortunately we can read the text. Oh, there's the table. Ha! So I've not seen that, but I've discerned it correctly for this particular input. All right, I think that's the half of the magic is how you encode the input in such a thing. And this seems to be, first of all, a pretty cool idea, but second of all, it exactly is what this kind of new regime of NLP is about, is that you basically put everything as a string, you annotate it in a smart way, and that lets the model figure out a lot of stuff about the input. People used to do the very different things. So people, if given a query and a table like this, what people would do is they would somehow, first of all, get the table headers and kind of guess the data types of the attributes, and then they would reformulate the query, maybe also with a neural network, maybe with something else, into something like SQL, in order to actually have an SQL statement to select the correct cells or perform the correct aggregations. And that is somewhat brittle, and it's just much less deep learning than this model. So I like this part of the model. Now the problem, of course, is, as we've seen, in this multi-step process. So how do we, first of all, if we want to build a cell selector, that's pretty easy, right? We've seen this. So the cell selector is first column selection, and then second row selection. And this can be multiple rows. So that's fairly easy. Selecting cells either for just returning or for aggregation, pretty easy. But how do we do actually the aggregation selection is also pretty easy, because we can just do a multi-class classifier, right? So the classifier will simply tell us, give us a distribution, and then we see, okay, the sum aggregation is probably here what the model wants. The real question is, how do we train this? And how this is trained is what I find really interesting. So as we've seen, they have training data. The training data comes in the form of tables, questions, and answers. As we've seen before, we don't know how to get to those answers. So when the question is, which wrestler had the most number of reigns, we just know the answer is Ric Flair. Now they do, again, a two-step process for their training data that mimics the two-step process of the model. So the first step is the answer a number? Is the answer a number? If no, then it is definitely a cell selection task. So if it's not a number, they just restrict themselves to selecting cells. If the answer is not in the table, then that just means that the correct thing is to select no cells and just say, I can't answer this question. If it is a number, then again you have two options. So, is it in the table? If yes, we are in a weird situation. If no, not in table, then it is an aggregation. Right. So if it is a number that is not in the table, that means that the answer is a number that is not in the table. That means the answer must be computed via one of these aggregations. And if the answer is a number but is in the table, then we are in this ambiguous answer setting where it could be that we need to select this cell, but it could also be that the same number by accident is in the table but actually needs to be computed from other numbers. And they do this in the most deep learning way possible, is that they do basically a soft decision here. So they let the model, when they let it select what to compute, they let it make a soft decision. What do I mean by that? So let's say you have these three operations: count, sum, and average. And you have the cell selection. So the cell selector will basically tell you, I will select 3 cells. The 3 cells contain the number 7, the number 8, and the number 3. All right, so, and the question was, I don't even know what the question was, but the cell selector tells you these 3 cells are to be selected. You do this by simply selecting the cells where the cell selector has a higher probability than 1/2. Now, your aggregation selection module gives you a softmax distribution over the actions. So it's not very much count here, maybe that's 0.1. This here is maybe 0.3, and this is the 0.6. What you do is you simply compute all of them. So you want to compute the count here, which is 3. You want to compute the sum here, which is 18. And then you want to compute the average, which, is 6. Ha! I made a good example by accident. And then you simply weigh the outputs here by their probabilities. So you say, since the model wants puts 0.1 probability on the count, I'm going to have 0.1 times 3 plus it wants 0.3 times this, so 0.3 times 18 plus 0.6 times 6. Now, I'm not gonna 0.3. So this is 6 plus 0.3 plus 3.6, 9.9. So that's how the model computes things. It simply puts probability on these operations here, and then you simply take a weighted output with respect to the computation of all those things. Now, I'm pretty sure that's completely invalid, because for the same numbers, for example, the sum is going to have a much larger variance than the average, and that's somewhat going. The count may be somewhere in between, depending on the numbers. So this, just to take the weighted average here, and then, of course, right? So what they do is they do have this. This is the model output, and you have the correct answer. Let's say the correct answer was to compute the average. So the correct answer is 6. So what they do is simply they take the squared error, and that's their loss. Actually, they don't take the squared error. They take a approximation to the squared error, which is square until some delta, and then it's linear. And this is simply to be a bit more outlier robust. And they do other things to be more outlier robust. But so this is the model output, and this is the correct answer. And they simply count on the fact here that this will backpropagate. So if you want to make these two things closer, if you're the model, right, you have the option of simply putting more weight from the other ones onto the average operation. And that will decrease the 9.9 because, as you can see, both of these numbers will get smaller and no, wait. This isn't the... Yes, sorry. So you will decrease these numbers. So this is the output we got from the weighted average, right? So if we decrease these weights, you will put weight from here to here. That will bring the number 9.9 down, and that will get you closer to the answer you're looking for. But you can also achieve this by, you can achieve this even more, right? So this 9.9 is too high. If we want to bring the 9.9 down, we're much better off by taking some of that output and actually putting on this here, because 3 is the lowest number, right? The only agreement here is that we want to take weight away from the 18, from the large one. So I'm extremely surprised that this works, given that it is so super ambiguous what the model should do with these operations. And I highly doubt that you can extend this set. So it's, of course, agnostic of what these aggregations are, but to be able to extend this to many more aggregations will, I think, lead to much more of these situations where the model is entirely unsure of where to put the mass, where to put the weight. And I would be interested to see what happens if you have a data set with like 20 or 50 of these aggregations and not just 3. So this is the let's say the interesting part here. If you go the other way, when you have this cell selection task, it is just to select a cell, right? And then you simply have the cell selector, that part here that does the selection, that you train every time simply to give each cell a weight, right? So this is simply the softmax over column and then the softmax over rows. And you can train that using the cross entropy. Now, training this cell selector from data is pretty easy when it's a cell selection task, right? Because the answer is in the table, and or is not in the table, and then you know to select no cell. So you do have the training data that a particular cell is the correct cell, and you can train the model to select that cell. But it is actually a pretty hard task if it is, for example, you're looking for an average operation, because not only are you not really sure that it's an average operation, you just know that that kind of gives you the correct answer. You also don't really know which cells to select for this average operation, right? Because depending on which cells you select, and of course that's going to be a soft selection as well, the average answer, the average will be different depending on which cells you select. So they're basically counting on this loss here to backpropagate not only through the selection of the aggregation to perform, but also to the cell selector to set which cells to select. So from this weak signal, it's almost like the reinforcement learning problem where you have the weak signal and you have like a billion ways to get your number closer to that signal, and not really accurate understanding of what you need to do. So you're just relying on the model through lots and lots and lots and lots of data to kind of figure out which natural language questions to map to which cell selection and aggregation. So it seems like impossible, but it works. The last thing we need to talk about is this ambiguous answer setting. And as you can imagine, it's pretty simple that they also let the model do a soft selection between the cell selection task, so no aggregation, and the aggregations to be performed, and basically let the model figure out itself which one is better, to do an aggregation or to do no aggregation. Suffice to say, this only works for I think it only works for pretty limited amount of tasks, pretty limited amount of questions. And you might have spotted there are even these questions that are follow-up questions, which are another thing they build into the model. And I'm not really going to talk about this, but they do have this concept as well, which I find maybe a bit out of place, but maybe it's just part of their data set somewhere. Maybe it's just these companies want to get into this conversational mode, so everything needs to be context dependent. The interesting part here is really the computation of the aggregates, and specifically the question of which of these aggregations to choose. And this, again, this is so surprising that it works, and fairly cool. I think that is the gist of the paper. They do extremely thorough evaluations here on these data sets and ablations to see what really counts and what doesn't. I don't really want to go into that. Safe to say their results are better than anything else before. I believe they're actually on par with another model, but in one data set, but they beat them on every other data set. So that's cool. I don't think there was a bar diagram. Never mind. I invite you to check out this paper. Look for yourself. They have the code online if you want to train a model like this yourself. Other than that, thanks for listening. If you like this content, please subscribe, like, comment, tell a friend, and bye-bye.